Okay, as I'm setting up here, very quickly, do you have any questions about the project? Anything? Again, more general questions, maybe not anything too detailed, but nothing. No. Then I have one quick announcement. Just that you're not surprised next week. Where are we? We are here. And we will actually be doing order n forward dynamics today. And we will be able, today, and we'll be able to finish it up, including the recap on Tuesday. At least that's my plan, unless something goes horribly wrong today. We should actually be done with this class by Tuesday, which I think is good, because you have a project to work on. And then what we will be doing on Thursday is that we're just here, or Iskander will be here, and we're doing an open office hour to answer your question. And of course, you can use that room. We will bring the power extensions. You can use the room to work on the projects and answer each other's questions. So that would be my suggestion. No reaction. Then let's dive in. Today's going to be fun, I hope. Fun for me, fun for you. Because we have an interesting puzzle. We looked at these beautiful equations that we derived, that, the canonical form of the equations of motion. And then we asked the question, how expensive is it to evaluate them? And the answer was, if you implement stuff verbatim as it's written here, this is how you do the mass matrix, this is how you evaluate your inverse dynamics, you're looking at something that's order n cubed in terms of computational complexity. 10 times the problem size, 1,000 times as slow. And then we started from scratch and basically did what you would be able to do after, in the case of the Uni Stuttgart bachelors, Technische Mechanik 3. You do a free body diagram. For each body, you set up the impulse and momentum balance, Impuls und Drallsatz, and you solve this recursively. And you basically start from a root to get all the accelerations, and then you start from a leaf to compute all the interaction forces. Right? You could have done this before taking a single class or a single lecture of this class. And the computational complexity is order n. Way better. Right? We then looked at an example, and don't be fooled by the example, because there n had to be 1,000, but that's mostly MATLAB, right? Because doing for loops in MATLAB is very slow if you do it in a script. If you do hidden for loops to do a matrix multiplication, it's super fast, simply because the code, the programming language, is optimized that way. If you would implement everything from scratch, if you would do this in C, your results would show much sooner, right? Maybe with an n of 2 or 3, that the Euler, recursive Newton-Euler algorithm is much quicker than evaluating the canonical equations of motion. Now, the question, of course, is why? Right? What's going on here? In a sense, why is doing this here so bad? And I written down an example here, which is a bit of a reduced version of a full inverse dynamics. I assume that gravity is 0. I assume that we're starting our system from rest, so I don't have to worry about Coriolis forces, bias accelerations, gravity, and so on. And I also ignore rotations, which you can interpret as these are point masses in 3D, or as bodies which have no inertia. And if we do it the way, well, someone taught you, the first order of business would be to compute your mass matrix, which is given as the sum over all bodies. N in this case is NB, and you do this evaluation JS transposed times N times JS in some coordinate system, typically body fixed coordinates. And we said doing this requires 3 nested for loops. I have here a partial mass matrix where each element of that partial mass matrix is basically 3 components of this Jacobian in a dot product with 3 components of that Jacobian and scaled with mass. So each element of that partial mass matrix requires 6 multiplications, 5 additions, sorry, 2 additions. Yeah, you get the point. 4 multiplications, 2 additions. But you have to do this for each element of the partial mass matrix, because what we create within the sum is an n by n matrix. And then you have to do this for each body, where this is n cubed, and this is n body. But we said they're bounded. If we just talk about computational complexity, it's 3 nested for loops with roughly n iterations, where n is somewhere between NB and 6NB, right? We don't really know, but doesn't matter. Scaling doesn't matter. Order n cubed. And then we compute the torque, which is that mass matrix multiplied with our vector of generalized accelerations. And then typically you would have gravitational and Coriolis forces, but in this example we simply set them to 0 to keep things a little bit simpler. And that's a matrix vector multiplication, so an order n square operation. And then the first step, of course, dominates our complexity, so the whole thing is order n cubed. This is what I taught you. But in terms of evaluating, you could do things differently and essentially first compute your accelerations. And for the simple case, right, since we don't have any bias accelerations, since we set q dot to 0, the accelerations of our bodies are simply just js times q double dot. What's the computational complexity of that? Js times q double dot. And just to be clear, right, there's a different Jacobian for each body. Matrix times vector, computational complexity. Do you say linear? Constant. But this Jacobian, right? So J, what are the dimensions of this Jacobian J? No. So what are the dimensions of Q? Well, NQ. What are the dimensions of X dot? For one single body? 3. Right? It's a linear acceleration. So a Jacobian Ji is a 3 by NQ matrix. So if I run this, multiply this matrix with the vector q double dot, I have 3 column times row operations. So column times row requires NQ multiplications. I do this 3 times, so I have 3 times NQ multiplications and then some additions. But you see, all of this scales with n. because I have the 3 here, right? It's not matrix times vector. This has more this nature of row vector times column vector. In a sense, what we're doing here is 3 dot products. So this is order n. But then, of course, I would have to do this for each body. So I would have to set up another for loop around this to compute xi for each individual body. And then what's the computational complexity of the overall process? N squared. Right? Then we have an outer for loop to go through the indices I for each body. And we have an inner for loop that goes through the indices of this vector q double dot. Then, next step, I compute, based on these accelerations, I compute my D'Alembert forces, in this case my change of linear momentum, which is simply mass times acceleration. What's the computational complexity of that step? M times xi for all bodies, right? It's here, this is just 3 multiplication. So if you would say this is constant computational complexity for one operation, n doesn't even show up. It's just the number 3 for the 3 dimensions. But if we do it for all, I have to do this n times. So computational complexity order n. I then have to do my Jacobi transpose mapping, where I say a particular D'Alembert torque creates a generalized torque that is computed as this Jacobian Js, now transposed times the change in linear momentum. What's the computational complexity of that? You say n cube. N squared for all. So this again is this idea of matrix times pardon me, this is actually, you should think of this as almost like a vector times a scalar, right? This has 3 elements, but I have to do this for each row, or if in the transposed form, each row of j, right? I multiply the row of j with this vector p. This is a 3 vector. The row has 3 elements, so that's constant time, but I have to do this for each of the nq rows. So this multiplication by itself is order n. It's, in a sense, a vector times a scalar, just that we're basically taking 3 vectors multiplying with 3 scalars, the 3 elements of pi. But then, of course, I have to do this for each body. So there's another for loop, and I get an overall computational complexity of order n squared. And then ultimately, there's one last step where I have to sum up over all these individual torques, right? There's one torque created for each acceleration of each body, and to get the overall generalized torque, we have to sum all these tau i's up. Computational complexity of that. Think about how many for loops do you need. So I need a for loop for the sum, right? I equals 1 to n, and this would be number of bodies, just to be precise. But we would just say n, because it doesn't matter whether we say nb or nq. So one for loop for the summing up, but then tau is a vector that is nq dimensional. So for each sum, we have to add nq elements to each other. So this is actually another order n squared operation. Two nested for loops. You would have an outer for loop that goes from I equals 1 to nb. And then for each, within that for loop, you have to add sort of your current running value of tau, and you add the next tau I. But there you add a vector to a vector. And these vectors have nq elements, so you have to do nq additions in this case. Right? So we would do here n square additions.
And the first method, if you separate the m's into mi's, shouldn't it be like the second method? And like first step will be computing mi, and second step will be summing them all. So it's going to be n squared.
No, this is first step, second step. You have to be careful when you say this, because sometimes things are nested and sometimes they happen in sequence. So with the recursive Euler-Forward algorithm, the recursive Newton-Euler algorithm, we get to the other one. Recursive Newton-Euler algorithm, first step, compute accelerations in one for loop. But then that for loop is done, and you have computed all the accelerations. Second step, new for loop, compute all the constraint forces and extract the joint torques. So two for loops happening one after the other. If I would implement this, right, I would have a for, so I would have a tau equals initialized to 0. Then I do for I equals 1 to n. In this case, n body. And then within this, I would have to say for j equals 1 to nq, and I would say tau of j equals tau of j plus tau I index j. End. Right? So this inner for loop just adds two vectors, which in MATLAB you wouldn't write this way. You would just say tau equals tau plus tau I. But in the background, you're adding two vectors, so you have to do this element by element. Right? And if I write this out in its full form, I get this nested for loop. And then I have to do this for each body. And this is why this sum, right, writing it down, the sum is a order n square operation. Did that answer your question? You're nodding and your face says no. What's still bugging? In M, yeah. But computing one of these is already order n squared, and then summing them up, right, means you're operating. It's basically, it would be the same argument, but here I'm summing up vectors, and here I'm summing up matrices. So to do this, I would add another for loop. This one goes, row by row, but then I would have to add a column index. So I would go jk with another for loop. What's the overall complexity of the stuff on the right-hand side? N squared, right? So it's just the maximum. So this is order n squared. And by now, you should see that we're actually doing exactly the same thing. That here I first compute the mass matrix, then sum over the individual mass matrices, then do the multiplication. Here I first, I basically write this out as, in a sense, directly as, what just happened? In a sense, I write tau equals sum over j transposed mi j q double dot. And the way I evaluate it is I start with this, then I do this, then I do this, and then I evaluate the sum. And what you see is nothing else than this idea that we looked at in MATLAB in the last lecture, where I say if I have this triple product of 3 vectors, which go row times column times row, the stupid way is to first multiply row with column, exactly the other way around, column with row, to get a big matrix, and then multiply it with a column vector. And the smart way is to first evaluate the dot products to get a one-dimensional scalar quantity and then scale the vector. And we do exactly this. The only difference is we do it n-body times, right? And if you first compute your mass matrix, you're basically going to this high-dimensional quantity, which then gets multiplied with a vector. If I do it this way, same in the end, it's the same result, right? It's the same equation. In both cases, I should put this in the middle, because in both cases, left and right, we're evaluating this expression. Just in one case, you don't have to copy this, I just want to highlight it. In one case, we do it in the smart order, and in the other case, we do it in the stupid order, where here we would first do this, we would then do the sum, and at the very end multiply with this matrix. And that's just unfortunate sequencing that makes the whole algorithm slow. I hope everyone sees that, right? And it's just an example of this idea here. Nearly verbatim. Questions? So we brought our canonical form down to order n square. There's still room for improvement. And where does that come from? And I already state here, cryptically, recursion helps. And let me maybe phrase this as a question. If I have a robot, and I do our usual just kinematics chain, and it has a bunch of joints, so Q1, Q2, some Qi, up to a Qn. And I am interested in computing the acceleration of my end effector. What is the computational complexity of computing the acceleration of the end effector, this xn double dot? What do I put here? Order. N. You would start at the root and you just do our outward pass algorithm, just as we discussed with the recursive Newton-Euler algorithm. Compute the acceleration across joint Q1, compute the acceleration across joint Q2, and each of these computations is basically the same amount of work, and you have to do this n time once for each joint. So this is computational complexity order n. If I extend this drawing a little bit, right, and we just basically saw this, that I have to also maybe think about the accelerations that we have in other places. So there would be a, this would be xi, this would be x2, this would be x1 double dot. What would be the computational complexity of computing all of these accelerations, right? If computing one is order n, what is the computational complexity of doing all xi? Also n. Simply, just in order to compute the acceleration xn double dot, you have to compute the accelerations of all other bodies prior to that element in the chain, just to get xn. So it doesn't matter whether I only want to know xn or I want to know all of these. And the idea here is basically, this is order n. Since we need to first compute well, xi double dot, x1 double dot, x2 double dot, xi double dot, and so on. And that directly implies that if I want to compute all accelerations, I actually have done this. All I have to do is basically reuse these results or store these intermediate results. So, what do you think? Do you like Jacobians? What was your impression throughout this class? Maybe Jacobians, wouldn't say the best thing since sliced bread, but definitely high on my list of things that I like. They're really stupid. Because if you look at this, right, why is this order n squared? So I'm computing here, right? I'm saying I compute all xi double dot in order n squared time if I use Jacobians. Whereas here I say it should be order n if I reuse my intermediate results. But what's going on? If I would implement this with Jacobians, I would start with the first Jacobian, which has a couple of elements in the first column, the one that corresponds to Q1, and a bunch of zeros down the road, because none of the other joints matter. So for the first body, this is going to be a matrix with elements in the first row, and then you're just multiplying stuff with 0. So you're wasting a ton of time multiplying things with 0. And then you get x1, right? And then you want to compute x2. You throw what you just learned away. You now have a Jacobian, which has 2 columns with stuff in it and a bunch of zeros. The first column, multiplied with Q1, is going to give you some information over x1 double dot, which we just computed and threw out. The second column is actually adding additional information. So I'm basically, if I do it this way, if I do it with Jacobians, I'm throwing away all these intermediate results, everything I learned so far, and start from scratch. Right? That, of course, is what makes it mathematically beautiful to write down, because I can essentially give you a closed form expression for each xi. Right? There's no sequencing, there's no dependencies. Looks beautiful, but it basically means you're throwing away things that you have already computed, and you start over. That's where this order n square comes from. So the trick here is basically, right, what we have to improve is this step and these steps, right? The summing of the torques and the computation of my x double dots. So if I basically, and this is now a comparison, step 3, if I compute all xi not with Jacobians, but recursively, I get an order n operation. And that's because computing the value for my last body, x and b, automatically means we have to compute all of them. And if I do it with Jacobians, I throw away this information and for each body basically start from scratch. If I do it recursively, I store the information, and for each body I just have to do the increment. And the same principle, without going into the details, but the same principle can be applied to our joint torques tau I. Right? Again, we have a projection with a Jacobian. But if we do it recursively, we get an order n operation. And here the idea is basically if I want to compute the joint torque at the root, so here in the example we will call this tau 1, the joint torque at the root, I first have to compute all the other joint torques. We saw this in the recursive Newton-Euler algorithm. I start on the leaf and then move inwards because I first have to know what's happening sort of down the kinematic tree. And a Jacobian would do this for me. I can write these as vectors because they could be joints with multiple motion primitives. The Jacobians do that recursion in a sense for me, right? Again, this Jacobian formulation, it's very elegant because I can get all the joint torques that are created by an individual force. Very useful when you do gravity compensation. There's one force and I want to know all the joint torques, right? And I can do this with one multiplication here. But if I want to compute all the joint torques that are generated by all the in this case, inertial forces, it's better to sum them up recursively because stuff down the chain influences things closer to the root. If we talk about forces, and then if we talk about accelerations, it's exactly the other way around. And because of that, we can break this down to an order n algorithm. That basically changing the order allows us to go down to order n square, or the order of computation allows us to go down to order n square, and then not using Jacobians, but doing these calculations recursively gets rid of an order n square. Do you have any questions so far? Are you ready for the next puzzle? We've now discussed two algorithms, right? Basically what we implemented in class, which I think has some educational value, and this is why I stick to these algorithms, right? To make sure you understand what's going on, and then also being honest and showing you where they suck, and how a recursive Newton-Euler algorithm can be better. In all other classes, you've done something else, right? You haven't even written algorithms. You typically derived equations of motion analytically. And then you got an analytic expression. And when you ran a simulation, you would just substitute your variables for specific numbers and evaluate that. What do you think? Where does that end on the spectrum? Is that good? Is that bad? Is that computationally efficient? Shall we give it a try? You can, what's your opinion, right? It's just guessing, so there's no right or wrong at this point. Okay, sorry. First repeat the question, and then I restate your answer. How good is it to derive the equations of motion analytically, and then just substitute variables for numbers and evaluate? This is what you have your equation, plug in numbers, get a result. How good is that compared to the two algorithms that we just discussed? And your answer depends on the number of degrees of freedom. That's a no answer, because what I want you to give me is how it depends on the number of degrees of freedom, right? Is it order n or order n cubed or something in between? Right? If I would derive all of this analytically. Yeah, let's give it a try.
Do we drive the equation of freedom or the MATLAB drive?
I'll show you. Sorry, this is there's so much scrap open. Pardon me. Here we go. This is the same example of what I showed you in the last lecture. Same n degree of freedom robot with sort of the structural difference that I do small n, because if I derive stuff analytically, it very quickly becomes a little bit hard on the symbolic math toolbox. And then instead of doing one evaluation, I do 100,000 evaluation. Is that a lot, 100,000 evaluations? Okay, I'm a roboticist. Is that a lot for a roboticist, 100,000 evaluations? If this is a controller that runs at a kilohertz, this is, a minute and a half of what your controller has, or of your controller's life, right? So in robotics, when we do these things, we often think of doing them hundreds or 1,000 times a second, because there's a control loop which typically runs at I don't know, somewhere between 1 and 10 milliseconds. So this is actually not very unrealistic, right? How do we do it? We define everything as symbolic variables. So I define my vector q as a symbolic variable. I have my parameters as symbolic variable. And then I do here sort of my, in this case, recursive computation of my kinematics, right? So starting from some initial value, I compute the orientation, and based on that orientation, I compute my positions. And once I have that, I then compute my Jacobians. And if I let that run until this point, nope, that's not what I wanted to show you. Where's MATLAB? Oh, it's gone. Hello, MATLAB? Here we go. You see what I meant before by recursion, right? If I look at just at the angle of each segment, and this is simple because it's a kinematic chain, the last element is the sum of all joint angles. But to compute the orientation of the last element, well, I could just evaluate this equation, or I could just take that previous result and add Q6 to it. So there is sort of this recursive nature, just the way we think about this as kinematic trees. And then you see sort of this triangular structure also if you look into positions. That stuff that is sort of closer to the root is simple, and stuff that's further away from the root gets very complicated. It's not scientific, but I'm just trying to illustrate things here. And then I initialize my mass matrix, and I let it run. Build up the sum here, and this is my mass matrix, and now you don't see anything, and this is where we pull out the really recent tools. I think even my first version of Microsoft had Notepad, and I'm not telling you how old I am. But you get a bit of a visual impression of what's going on here. This is the analytical description of the mass matrix of a 6-element planar robot. Let's do a little bit of compression here. Let's replace all the empty spaces. So what do you say? 4 pages of code. This is my measure for complexity. Let's see how quick it is. And what I did here is I actually don't compare this to a numerical evaluation. But what I do is I define some parameters now as numbers. And what I do is I evaluate this now 100,000 times. And I have two different ways of doing it. One is called a direct evaluation, and one is called a MATLAB function. And both of these are just wrapper functions. I could have done this with anonymous functions, but I find these a little bit confusing sometimes to read. One is called M function, and one is called MMAT. And they are both derived from this analytic expression that I just copied into Notepad using MATLAB function. And I've done it two ways. One is I created an anonymous function handle. Two is I created a file, just to see if that makes any difference, right? Either have the function stored in memory or have the function stored in a file, which is probably what you would do when you ever create this, right? You would have this somewhere as a separate program. Which is quicker? What do you think? Let's give it a try. Sorry, not this way. I need to run my profiler, run in time. Not touching anything. Here we go. So we did 200,000 evaluations in roughly 7 seconds. So you can break that down, right? If this is my controller, if you implement stuff in MATLAB, how much time do you just spend on computing a mass matrix? And if you want to do this now 1,000 times a second, what percentage of your controller evaluation time goes down the drain for this? I want to look at this again, just simply line by line. And you see that the analytical computation, there's nothing sticking out other than putting stuff on the screen, right? None of this is really expensive, but then you spend half a second just to write out your mass matrix. That always gets me. That this is the slowest bit of your code. And I had this in cases where actually, I had a lot of debugging information and I disabled it and my code ran 10 times as quick. Then I generate these two functions. I do the anonymous function handle, which is stored in memory, and I do the file. And that file, creating the file takes surprisingly long, right? It has to be stored to written to disk, of course, but does that explain the 2 extra seconds? There's something going on here. And then we do the evaluation, and we actually see that using this anonymous function stored in memory, just a function handle, 2.6 seconds, evaluating the function file stored on the hard disk, more than 2 times as fast. Why? Right? That's not what I would expect, right? Because for this, you basically, MATLAB is a little bit smarter, but you have to open the file, you process the content, whereas this is already stored in memory, part of the program. What do you think? Let's have a look. So, sorry, maybe general confusion. What was the question?
Wondering why the display is not now so much shorter than before, like this display of the mass matrix.
Oh, because this is just, sorry, I should have mentioned this, but this is now just putting down the specific numbers, which is 6 by 6 numbers, and the other was 4 pages of characters, plus all the empty space that I removed. So the nice bit is we can actually look at what MATLAB generated. So this is the auto-generated file that we just put onto memory, and it's reading out the parameters and the states from our 2 input variables. So this would be P and Q. But then what we see is these temporary variables or intermediate variables. And you see, for example, there is a T4, which is Q1 plus Q2. So that's phi 2. And then where does it show up? Sorry, I have to look here because I might be missing it. This one here. T12 is T4 plus Q3. So somehow MATLAB figured out that there's a recursive scheme, that this expression Q1 plus Q2 that we saw here shows up multiple times, and rather than computing it 1, 2, 3, 4, 5 times, it computed it once and then reused that intermediate result. So MATLAB somehow automatically figured out that there is a recursive structure and used what is called code optimization to exploit that recursive structure. And that sounds fancy, but it's just pattern matching, right? Anything that shows up more than once, it makes sense to put in a temporary variable and then replace that instance everywhere with this temporary variable. And you can quantify your gain by going ahead and putting this in, again, in Notepad. And so this is the analytical function that I just copied from the MATLAB output. This is the optimized code, right? And none of this is scientific, but if you somehow believe that numbers of character relates to the number of operations that have to be done, you can already see that this is way quicker, right? We have maybe a quarter or even less of the symbols that we had before. We don't get that full gain because, of course, there's some advantage of having the function in memory and not, opening the file. But that explains why in the profiler we see this big advantage for the functions on file. And I find this interesting, right? It's basically gives you an intermediate answer. If we create an analytic expression, depends on how we create it, but it may not, we may not realize that it has a recursive structure. So we basically wrote something just the way we wrote it down that is more of an order n3 computation. It would be interesting to, maybe I do this someday, to do this for different NQs and then just count characters and plot NQ versus number of characters, and then you would see, do I get a cubic curve or a quadratic or something? But it's not something linear. But then MATLAB goes in and does its code optimization and somehow realizes, oh wait, I'm reusing stuff. Things there, I do pattern matching, I can use things multiple times, and that significantly then cuts down the computation time. Just a fun example or a fun side note to maybe once you have your algorithm, once you have your math written down, think a little bit beyond that, because writing it down and evaluating is not the same thing. So, questions? What we've established so far is now that we can do inverse dynamics in order n complexity. We can compute a mass matrix. This is basically what we did in the examples, in order n squared complexity. Right? We will not be able to do any better because we have to write it down, the mass matrix. What about forward dynamics? Right? So far, everything we did was inverse dynamics. But forward dynamics would be a simulation where you say Q double dot equals M inverse F plus G plus tau. And we could compute the mass matrix using the recursive Newton-Euler algorithm in order n squared time. But now we have this guy here, our matrix inversion, which is, I say, roughly order n cube complexity. I have this table, which I copied straight out of Wikipedia and which is probably in your template, if I'm not mistaken, that has a sort of, if you do a Gauss-Jordan elimination, is probably what you learned in your numerics class. It's exactly order n cubed because you have to go, you do these row pivots, and for each row that you want to get rid of, you have to move once through the entire matrix. So it's n operations on a matrix, so n to the 3. And cube operations, and there are some specialized algorithms that actually are a little bit faster, but ballpark, let's say order n cube. So what's the best that we can do for a forward dynamics algorithm? How good can we get, right? Just computing the mass matrix is order n squared. Can we do it in order n squared? Is there a way to get around the inversion? Is there a way to get around the mass matrix? If you cheat a little and look on the next page of your templates, you see that there's something called the order n forward dynamics. So there actually exists an algorithm that allows you to do forward dynamics, which requires, for everything that we discussed so far, requires an inversion of a mass matrix to do that in linear time. And that's the last thing I want to discuss in this class today and on Tuesday, because it kind of nicely ties everything together that we've done so far. It talks about computational complexity. It talks about projection methods. It talks about different spaces. It's a very nice way to sum up and wrap up this class. And it starts with an idea that is called the articulated inertia. To imagine what the articulated inertia is, you have to go into my lab, take a screwdriver, and go to our humanoid robot and screw off its leg, and hold the leg by what used to be the hip joint. And then you shake the leg. Right? So you're moving not a rigid body, but you're moving an articulated object. So something that consists of multiple bodies in some tree structure connected with joints. And what you do is you grab one of these bodies, right? You could grab the robot leg by the foot, you could grab it by the pelvis. Whatever body you choose, we're going to call this the handle. That's the body that you grab. And now you apply an acceleration to that handle. And I express this here as the acceleration of the center of mass of that handle. And then, of course, since this is 3D, you can also apply a rotation. And the question I ask is, in order to generate that acceleration of the handle, what force and what torque, F and M, do you have to apply? And now I make a very bold claim where I state, and I really just, for now, this is just an unsupported claim, where I say there's going to be some matrix that depends on Q. And that matrix is going to be a 6 by 6 matrix. And we will multiply it with the accelerations that we apply. So BAB would be the acceleration of the center of gravity of our handle of body B expressed in B coordinates. And then we have our angular acceleration of body B expressed in body B coordinates. I subtract from that what I call a bias force, which also gets these sub-indices and a little hat on top, because it's a 6-dimensional quantity which has units of linear and rotational accelerations. And this bias force will depend on a bunch of things. Let's leave this open. So there's 1, 2, 3, 4, 5 things that go in there. And that is equal to the force that you need, right? So this would be the force expressed in B coordinates and the torque about the center of mass, again expressed in B coordinates. And that's just a claim, right? And what I basically say is that that force is linear in the accelerations that you apply, right? There's a coupling, so it's a 6x6 matrix. There's a coupling of rotation and translation. And there's a bias vector that does not depend, and that's important, does not depend on accelerations. What's that bias vector? Well, I think that's easy to figure out, because if I set the accelerations to 0, I would basically see that the forces that I have to apply are minus the bias forces, just to keep things stationary, right? And if I think of just grabbing the robot, if I set the force to 0, so I let it go, the acceleration is not going to be 0. What will happen? 2 things in sequence. Number 1, robot leg will fall to the ground. Number 2, whoever needs this robot for the experiment is going to kill you because you just broke the robot. So there has to be some bias force. You grab your robot just to keep it stationary. That bias force depends on bunch of things, right? Of course, external forces, gravity, any external moments, anyone pulling on that robot, gravity pulling on that robot is going to generate or going to require a bias force. Those effects are, of course, dependent on joint angles, Q. But maybe this articulated leg, it's still wired up and it's moving. It has motors, they're moving, so there's motion. I'm not talking about accelerated motion at this point because we're trying to do forward dynamics. If I ever write down Q double dot, right? Q double dot is what I want to compute at the very end. Here, what I can compute from Q dot are going to be bias accelerations, so centrifugal acceleration. You can imagine if the leg is spinning at constant speed, it's going to create some acceleration that the person holding the robot leg has to balance. And then if I have motors and I supply motor torques to these motors, that's also something that I will feel on the handle. So this is basically my idea. That we have somehow a linear relationship between forces and accelerations. And to some degree, this is not something new, because when we talked about contact and collisions, remember how we basically had our articulated robot, and then we had a contact force, which was not someone grabbing the robot, but in a sense ground pushing against the robot, in this case in the integrated form of the equations of motion. And that created a acceleration, or in the integrated form, a jump in the velocities in the same space, right? So I applied a lambda in contact space, and I got a change in velocities in the contact space. And the relationship between these two quantities is purely linear, right? We had this contact space mass matrix. that got multiplied with the change in velocity, so the integrated accelerations, and then gave us an integrated force. And here I'm basically making the same claim, almost exactly the same claim, just that I say my contact space is sort of this 6-dimensional quantity of the accelerations of the center of mass and the orientations of the body. And then consequently, my lambdas are these corresponding forces and moments. And I'm not looking at this in the integrated form, but I'm looking at this as a continuous process, which is why all these bias forces show up. Right? When we derive the collision equations, at some point we say integral over fg is 0, integral over tau is 0, integral over g is 0. Now here they will still show up as a bias force. Now, the big thing that we cannot do is compute this mass matrix m lambda, which corresponds to this articulated inertia ma, the way we did it in the previous chapters, because to compute m lambda, we first computed n, which is an order n to the 3 operation, and then pre-multiplied and post-multiplied with Jacobians, which is another order n square operation. So we need a different way to get in here. But I hope you believe that this is at least feasible, right? That for the system that lives in this space where we know the joint torques, we know the external forces acting on it, we know the velocities of the joints, we will be somehow able to set up a system like this. And I want to now introduce a new notation which will abbreviate things a little bit. I will summarize and write these 6-dimensional vectors as a single vector with a hat on top, and I will call this a spatial acceleration. And at the same time, I will do this for forces. So this will be a spatial force, a combination of force and moment. Sometimes in the literature, this is called a wrench, right? Something that rotates and translates or creates a force and a torque. And this would be called a twist, or the derivative of a twist, but somehow related to a twist. And each of these quantities has 2 indices, where one is basically our standard index for a coordinate system, and the other is our reference point. So in this case, the center of gravity of body B, and everything is expressed in body fixed coordinates. And then this guy here, I already said I will call this the bias force. And in short, I can now go ahead and write an equation that reads ma, the articulated inertia, this is how I will call this. The articulated inertia is the spatial times the spatial acceleration is going to be, and now I just rearrange things a little bit, is going to be my wrench that is acting at the handle plus this bias force, PA, which I already wrote with a hat on top because it's this combined vector. If we work with these vectors, we have to think about coordinate systems and reference points at the same time. So if you imagine I have a force set up that somehow creates a torque, an effective torque on my body about a point B1, that is equal to an effective moment about a point B2 plus some additional moment that is created by this force. And we get that via the cross product of the lever arm from B1 to B2 cross F. So a force F plus a moment B2 can be expressed as an overall moment about point B1, taking into account this lever arm. So I'm basically moving the force, which on the right-hand side, or is acting at body B2, I'm moving that force into a torque about point B1. Versatzmoment in German. So that means I can write, and now I have to be careful that I don't screw this up. Yeah. Let's write everything in B2 coordinates, but what I can write is that the spatial force about a point B1 can now be written as the following matrix. We have the identity, we have a 0, we have this vector R, B1, B2 tilde, and this now needs to be expressed in a coordinate system, which is the B2 system, of course. I have identity here, and I multiply this with my force, spatial force vector, still expressed in B2 coordinates, but now using B1 as a reference point. Using B2 as a reference point. And you see that what I say here is basically, if I change my reference point, the force effect is going to be the same, but that force is going to create a moment. So if I have a different reference point, I have to take that into account. And I can write this as a linear transformation. I can, along the same lines, think about a coordinate transformation. If I want to go from one coordinate system to another, and this one is now easier because all I have to do is I take a coordinate transformation on the force component and a coordinate transformation on the torque component, and those two are of course the same. There's no coupling, and I simply have to multiply my vector in B2 coordinates with this matrix to get my vector in B1 coordinates. And now I can put these two steps together and basically change coordinate system and reference point at the same time. So F of B1 as reference point expressed in B1 coordinates is going to be this transformation matrix, the 6-dimensional transformation matrix, which is just two 3-dimensional transformation matrices applied at the same time, pre-multiplied with this change of reference point matrix, which involves here our cross product expressed through the tilde operator. And the whole expression gets multiplied with our spatial force vector with B2 as a reference point and B2 as a coordinate system. And then I'll give this a name, and I call this AB1, B2, but for spatial quantities, so I put a hat on top. And I can simply say this is A, B1, B2 hat times F in the B2 world. Any questions? Just a shortcut notation, but we will later jump from body to body, and if we jump from one body to another body, we have to change the coordinate system and we have to change the reference point, so these are going to be important. Now I'm running out of space, so I have to compress this a little bit. Pardon me, but you have copied it already. Yes, go ahead.
The last term, I get the transformations on top, but like the third one, why is there two like I get this one and the one next to it, but like the third one, B1 F B1 relative to B1. Why is there two transformations multiplied by the F B2?
It's just a definition, right? I have to change my force and I have to take my torque. And if you think of these as two independent 3D quantities, each of them has to do a coordinate transformation. And that's all that happens, right? And this is why I have this block structure. This is basically transforming that force. This is transforming that moment. And that's it.
And the third term, why is there two like matrices multiplied by each other before?
This one?
Yeah, no, the one below it. Yes, this one.
Now I do both in one step, right? This is my changing the reference point, and this is my changing the coordinate system, and I basically first do one, then the other. I think I did it here in the wrong order. No, this is exactly right. So I basically first do this, and then that result is plugged in here, so I can just multiply the matrices with each other. So all checks out. I thought I did this wrong. So why is this fun? Because you can think about velocities the same way. So if I think about 2 points on a body, and we've seen this equation, the velocity of point B1 on one body is going to be the velocity of point B2 on that body, plus then we had this cross product omega cross the relative position between these two bodies, RB1, B2. This is chapter 3, relative positions of velocities of 2 points on a body, and there we called them P and Q, and here I call them B1 and B2. And I can write this as VB2 minus the cross product RB1, B2 cross omega. And instead of a cross product, I'm now going to write a tilde here. And instead of a tilde and a minus, instead of a minus, I will do a transpose. So this is exactly the same with my now vector omega. And now I can go ahead and say, okay, in spatial representation, the velocity of, I have my indices wrong, sorry. I flipped them up here. Please don't be mad. This should be B1, B2, and this should be B1. Otherwise, this is wrong. I could have flipped them here as well, but I want to continue with B2. So if I now think about this as a spatial quantity, I get a very similar matrix, because if the points are on the same body, I will just have the identity for angular velocities. And for linear velocities, we just saw that it's going to be the sum of the linear velocity plus the angular velocity times this matrix RB1, B2 transposed. And that would be the velocity of point B1, still in B2 coordinates. And I can now also do the coordinate transformation. So I just copy this matrix. And do the coordinate transformation. And I'll write this as AB1, B2 transposed. So what I want is AB2, B1, but these are orthonormal matrices, so I can just write the transpose here. And then multiply this with my velocity of point B1 expressed in B1 coordinates. And if you look at this guy and compare it with what we had up there, you immediately see that this is A, B1, B2 hat transposed. Right? Order is flipped and each of the submatrices or each of the individual matrices are transposes of each other. So I can just write this as A, B1, B2 hat transposed times the vector with respect to point B1 and expressed in B1 coordinates. So it's kind of useful, right? That we maintain the same properties. Again, this is very close to a Jacobian, so we shouldn't be surprised, right? In the past, we would have called this a Jacobian. But here, I think of this as a coordinate transformation and a change of reference point. For accelerations, and I do this without proof, something similar holds. I would have this Jacobian AB1, B2 hat transposed times the original velocity, original acceleration, plus some bias terms, some sigma that I will not further specify, that then depends on other things, but only velocities. All right, just notation. That was the boring bit. But it's always nice to see certain structures reappearing. And here we kind of nicely see the transpose in coordinate transformations. Now, I want to prove that what I showed you here, right, this is just a claim so far. I want to prove that this is true. And I also want to give you an algorithm to compute this MA as we go along. And I want to start with a single body. For a single body, I now have to write this expression or this relationship between accelerations of the center of gravity, angular accelerations, and the forces that are acting on this body. I have to write that somehow in this form. All right, so this would be the force on the body. This would be the moment, in this case, about the center of gravity of the body. And then we could identify these individual terms as the articulated inertia of a single rigid body, the spatial acceleration of a single rigid body, the bias forces, articulated bias forces of this body B, and then basically the forces on the handle, which we called F hat. Well, this is a single rigid body. So for linear motion, what I know is that F equals m times a. To compute m times a, I have to take this acceleration here and multiply it with m. And I'll do this not as a scalar value, but I write it here as a diagonal matrix of m's. The rotational motion is not going to influence the linear motion. And then on the right-hand side, I have my active forces, which are assumed to act on the center of gravity. And I have here my external force F. And if you multiply this out, your first row is going to read m times a equals Fa plus Fb. Simple equation of translational motion. And the same we can do with the rotational motion, where we have, instead of mass, we now have the inertia of body B about the center of gravity. So inertia times angular acceleration equals, and then we have the active force, active torques, ma, about the center of gravity of body B, plus the precision moment, which we computed as this term omega tilde times I times omega as a vector. So this is the change of angular momentum that comes through the change of the inertia. And again, that line gives you exactly your Newton-Euler equations of rigid body motion. And that is a good starting point, because what it basically says is if I just look a single rigid body, this is true, right? If I think of this concept of articulated inertia, mass times acceleration is some bias force that doesn't depend on any Q's, on any Q double dots, plus sort of the force on the handle. So what we want to do next is we want to connect handles with each other. And you can imagine how I build this up, right? I take two individual bodies, connect them to get an articulated body that consists of two bodies. And then I connect that body to an articulated inertia of another single body. And I have three bodies. And I can sort of build up my system by connecting handles. The way I will explain it is actually in the opposite direction, where I think about what happens if we break apart handles. So here is in blue my handle, and that is connected to other parts of this articulated body. And one of them I'll draw here in green, because this is where we will break stuff apart, and then there can be more to come sort of down the road. On the left-hand side of that drawing, I'm basically interested in saying if I want to generate a particular acceleration a hat, what is the force F hat that I have to apply? And I don't really care about what's going on in this other body. So this would be B, my handle, and let's give this guy a name, so call this C. I can split this apart into two individual articulated bodies. And I would have articulated body 1 with handle B, which is the blue guy plus the stuff directly attached to the blue guy. And then I have an articulated body 2 with handle C, which is the green guy with the stuff attached to it. Here's the center of mass of body C. Here's the center of mass of body B. And this transition from left image to right image, you can think of in the classical sense as a free body diagram. I'm cutting a system in part, and if I do that, I have to replace the physical connections with the forces that are transmitted through the physical connection, which means that the diagram on the right is not complete. I somehow have to account for the fact that there's actually a joint, but in a free body diagram, I would do this through interaction forces. And since this is a 6-dimensional connection, I'm going to write that as a 6-dimensional wrench. Here called FC, we also call this FJ, because what this wrench combines is the active forces, so motor torques in a joint, and the constraint forces. And together they're going to be a 6-dimensional quantity, but some of them are activated, some of them are passive. But if I cut this thing apart and say there's a joint, I know that there have to be 6 quantities. Some of them may be tau, some of them may be true constraint forces. So going from this drawing to this drawing, I think is fairly clear. If we connect two bodies, we actually want to go the opposite direction. So basically, we have to say we know that these are articulated bodies, and we know that body 1 has an articulated inertia of ma1, and there is an acceleration which is of course still ab, right? Still the same acceleration as in the left picture. When we do a free body diagram, these accelerations don't change. And that mass times acceleration is going to be equal to some bias acceleration, bias force, plus the force F here, and then we also have to account for this guy here. And the idea is basically, if I think of this as a handle, in the past we basically said there's just the green force acting on this. But now I also consider this to be an active force. So the sum of these two is basically what creates the acceleration AB. So I will include this here as well with the minus sign. So this is the constraint force FC, and I will express it as a spatial force that is acting on the center of gravity of body B, and that is expressed in B coordinates. Similarly, we know something about body C, or the articulated body 2 with the handle C. This guy has some acceleration that is going to be called AC, acceleration of this body C, expressed in C coordinates, and that times the articulated inertia of this articulated body is going to be some bias acceleration, bias force for body 2, plus the force acting on the handle, but the only force acting on the handle is the blue constraint force, right? So instead of a green external force where we said I grab the robot, I hold it, it's now the constraint force, Fc, that is grabbing and holding the robot, but here written in different coordinates and with a different reference point, because now I think of everything acting at the center of gravity of body C. So this is given somehow, and we can always say these are not articulated bodies, but these are single bodies, and if they're single bodies, we could just use these quantities to get ma1, ma2, and the bias accelerations. So somehow the black quantities are given. The accelerations, forces, they are unknown, but we don't need to eliminate all of them. We just want to basically combine these two equations to state a new equation, which basically says that my combined articulated inertia times the acceleration of body B is equal to the combined bias force plus the force with which I probe the handle. So in a sense, right, this is the equation for the situation on the left. These two equations are the two equations for the situation on the right. And I somehow have to manipulate these equations into that. And you see that to that end, I have to eliminate two quantities. I have to eliminate my constraint force, the blue stuff, and I have to eliminate my accelerations, right? So I don't know the accelerations of body C, and I don't know the constraint forces Fc. This is where I want to stop for today. I'll continue with this on Tuesday, how we can basically move from these two equations to that. But sort of the big picture, I think you already see building up. I can do this for individual bodies. If I can combine those into a new one, I can step by step create any arbitrary articulated inertia and through, in a sense, induction prove that this general structure that we just proposed here is true, that I have a linear relationship for each handle between acceleration and forces. Have a good weekend. Let's continue this on Tuesday. Thanks.